Good morning. Nice to have you here. Happy Friday. Today, in the lecture, we will officially start the review for the first midterm. Now, again, today is not the midterms, just to make sure that's very clear. The midterm will be next week, Friday. And I'm just starting the review now and stuff to give you a sense like how this all works out. Today, in lab at 1:10, we'll turn in the nomenclature lab from last week, the naming lab. Problem set number 3 will be up. We'll talk about that, which is also some nomenclature. Quiz 3 will have questions from problem set 3. And the empirical formula in class lab will happen. This is a lab where you've got to have some type of safety protection. So if you have goggles, absolutely bring them. If you don't have any, don't panic. I've got some you can borrow and stuff. It's not a big deal. But we're going to have vacuums and flames and acids. And it's kind of fun. Yeah. It's getting excited up here. I love it, man. I know. That's totally legit. So, yeah. So it's a fun lab. It went well on Wednesday and stuff, so it should be cool. On quiz 3, as well as the midterm, you are absolutely welcome to bring a notes sheet like we talked about on Wednesday. And the note sheet, one regular size piece of paper is cool, front and back, but don't have anything bigger because our desks aren't that big. You can have a note card, only one note card though and stuff. That would be fine too, whatever you want. And anything you handwrite, you can put on there. And I loved your questions on Friday. Or Wednesday, excuse me. They were all really good. But yeah, literally, if you handwrite something, it's fine. Don't take someone else's note card and use it for your own. Don't use any kind of computer-generated diagram. Things from the book and stuff like that are not allowed. But if you have your own, no problem.
Presumably, couldn't you technically use 4 note cards?
No, only one.
There's 3 by 5.
Only one. That's the rule. One piece of paper. So that's why I would use the 8.5 by 11 because you'd have more surface area, of course. But yeah, only one, man. No, you can't have more than one. We're just going to staple one thing to the back.
Somebody uses like you know they have the cards, the 3 by 5. You know,
you're right.
They have those, but in half. So they have like 8 note cards that they just staple to the back of.
I would charge you some points for that. So yeah, so just one thing. I'll give you a piece of paper if you'd like one, okay? So yes, a computer-generated algorithm. No, just one piece of paper, no bigger than 8.5 by 11. We'll call it and stuff. But I love the thoughts, man. Anyway, yeah, you can include that today on your quiz. You can also include something like that next week on your midterm. You do have to turn in this note page with whatever you're doing. So you have to turn it in with quiz 3 today or turn it in with the midterm next week. I will return them to you, but by default, I won't return them until the following week. So just think about that as you go through. So in addition to calculator, pencil, a note sheet for next week, bring your completed lab we're going to do today, the empirical formula in class lab. Exam prep worksheet is going to happen next week too. And like I was kind of talking about, the exam prep worksheet, I'm hoping, is not a big deal for you. It's a series of questions, about 5 questions, and the question is given, the answer is given, and you just show your work, how you go from the question to the answer. So you know what the answer will be. You just kind of show the steps in order to get there. And again, I'm hoping that this isn't a big deal, but Aiden says, wow, number 2, I don't remember this at all, Russell. No worries, reach out to me and stuff. We'll figure this out together. I want you to know these skills before the midterm, just to kind of make sure you're ready to rock and roll on that. Next week, also bring, when you come next week, Friday, the % potassium chlorate in class lab. You'll need a copy of that. We will have a lab after the midterm. Sorry about that. That's the way that rolls. And for that lab, like this week's lab, you will need some safety goggles. We're going to have flames and all kinds of stuff. This week's lab is, I think, a little bit more exciting. Lots of different pieces going in together. Next week's lab is kind of just hardcore flaming. Anyway, you'll see what I mean when we go through all this. The format of the midterm will have 20 multiple choice questions, 4 short answer questions, and it's about 2 hours. It goes from 1:10 to 3 o'clock. I highly encourage that either on our website or in the companion, you look at the sample midterm. You can get a sense of what an actual midterm like from a few years ago and kind of go from there. It's pretty cool. You'll take the midterm on Friday, and the following week, I'll return the midterm to you, and with that, you will get a summary sheet. And that just is another piece of paper at the end, and that's why I don't want you stapling multiple note cards to your thing. It would freak me out. But anyway, at the very end of your midterm will be this summary sheet, which is just how are you doing in the class as of today, all right? And you can check it out and make sure that the grades that are listed on there are the grades you actually have. If the lab is missing, absolutely turn it in, although this class has done really well turning things in. I'm very, very pleased. Any questions at this moment on any of this stuff? Cool. So what we're going to do now is just go through a series of possible multiple choice questions, or at least give you the flavor of multiple choice questions that you might see on the midterm. They're all iClicker questions, but you don't have to have an iClicker to participate. You can actually just do the work and then make a prediction what it's going to be on a piece of paper, and that's fantastic too. All right, so here's the first question. We got a piece of metal. Its mass is 33.2 grams, and it's placed in 10 milliliters or 10 centimeters cubed of water. And from this information, and from this diagram right here, see if you can figure out what the identity of the metal is. So I'm going to give you a few minutes here to work on it. And once I see some people who participated here, then we'll talk about what the answer is. If you don't feel like doing the problem, you can just sit here and think about what you're going to do later today or something, and that's fine too. But I do encourage you, of course, to think about it, see if you can figure it out. One person already has the right answer. The door is weird, though. Does anybody need more time? Yeah.
How long does chemistry happen in this class?
I don't know how
Like
long.
this classroom? Sorry.
Oh, like how long has there been chemistry classes in here? Oh man, I think since Mount Hood was built, which was 1970-ish and stuff. So I think this has always been a chemistry room.
Did that happen? From
That was Dr. Sherpa doing what's called the elephant chalk reaction or something like that, and it went up pretty high. And that's her stain. I don't hold it against her by any means. So, okay. Thanks, Chief. All right. So on this problem, this is kind of like what we did in the density lab. You're trying to find the density of a metal, essentially. It says identity, but identity in this case will be based on the density. And density is mass over volume. Now, the mass of the object is easy. You put it on a scale, no worries. The volume, you use usually what's called the displacement method, or the Archimedes principle. And what that means, you plop the metal in some water, and the change in the volume is what you're looking for. So in this problem, 22.3 milliliters or centimeters cubed, they are the same thing, was the final volume minus 10. So that difference would allow you to find the volume of the metal, and then the mass of the metal divided by that volume would be the density. And it looks like everybody did a pretty good job on this problem. It does come out to be 2.70 grams per centimeter cubed. And if you look at this list, that means it's going to be aluminum. Cool. Any questions on this one? No. Okay. Here's a question where we have 3 different temperatures on the Earth. One of them's in Celsius, one of them's in Fahrenheit, and one of them's in Kelvin. Now, Fahrenheit to Celsius is always strange, so I want to give you that equation right now. If you need to go from Celsius to Fahrenheit or Fahrenheit to Celsius, you take the Celsius temperature, whatever that is, multiply it by 1.8 and add 32 from it. And of course, if you have Fahrenheit, you can subtract 32 first, then divide by 1.8. But anyway, see if you can put these 3 temperatures in order of increasing temperature. So coldest first, hottest last. Let's see what you can do. People need more time on this problem. The strategy I would use on a problem like this is to convert this Fahrenheit and Kelvin into Celsius, all right? I'm all about doing the least amount of work possible, which sounds really bad, I know, but it's true. And the reason I'm doing that is because these are the equations I've been pushing for conversions. Celsius is what we usually record in lab, but Kelvin is what we use for a lot of calculations. And gosh darn it, we live in the US of A, so they report all of our temperatures in Fahrenheit, and it is nice to know how it correlates to Celsius. So what I would do on this problem, unless you're familiar with these scales, is take the Fahrenheit, the 45, subtract 32, divide by 1.8, and that will give you the Celsius temperature. You can then compare that directly to 29. Now likewise, I do the same thing with Kelvin. Now Kelvin, 256 Kelvin, equals the degrees Celsius plus 273, so you would subtract 273 from it. That's how I would approach this. You only have to convert Kelvin to Celsius and Fahrenheit to Celsius. You don't have to do more than one, etc. So if you did it, the answer comes out to be D. And in the steps right here, you can see this is totally what I did. So here's 256 Kelvin. I subtracted 273.15 and got minus 17 from it. And then likewise, here's the 45 Fahrenheit, I subtracted 32 divided by 1.8 or 9/5, whatever, came out to be 7-ish degrees Celsius. And 29 Celsius is certainly bigger than both of these, so that's the highest one. Really important to realize that Celsius can be positive, negative. Fahrenheit can be positive, negative if we use it, but Kelvin should never be negative for us. All right, it should always be a positive number. Any questions? All right. Metric conversions are another thing that we've got to talk about a little bit in these kind of classes. And these are all different conversions based on length, the meter. And so the question here is put these in order of increasing size. Now again, you can do this any way you want, but I would convert the millimeters and the centimeters into meters. So you can already see that 0.125 meters is smaller than 2.3 meters. If you had the same kind of numbers from the millimeters and centimeters, you can put them all in size. So see what you can do with this problem, and we'll go from there. everybody okay if I start talking about it? So on the last problem, I recommended converting Kelvin and Fahrenheit to like the central unit, Celsius. And on this problem, I would recommend doing the same. I would recommend converting everything to the base unit, which here is the meter. Now, milli is 10 to the minus 3, and centa is 10 to the minus 2. And these are some of the metric prefixes, and they work for any kind of base unit you want to use. So for example, a milligram is 10 to the minus 3 grams. But in this problem, a millimeter is 10 to the minus 3 meters. So if you have that one number up there, 215 millimeters, this is like a conversion, all right? And what it says, you can put a 1 right there, it says that 1 millimeter is 10 to the minus 3 meters. And the millimeters cancel out, and you've got meters. So if you do this, it comes out to be 0.215 meters. And you could do a similar thing with the centimeter. So 1 centimeter, 10 to the minus 2 meters. You convert 9 centimeters over, it becomes 0.09 meters. Anyway, if you do that, then you end up with this thing right here. So 9 divided by 100 essentially is 0.09, and that's the smallest of the lengths up there. Then the millimeters is 0.215 meters, so that's bigger than 0.125, but not as big as 2.3 meters. So that's kind of how these kind of problems work, and knowing these prefixes is pretty important, all right? Milli is one that we run into a lot. So again, it works for lots of things. So a milligram, 10 to the minus 3 grams, milliseconds, 10 to the minus 3 seconds, stuff like that. Any questions on that? Okay, this is now changing gears a little bit. It says, which of the following is not an isotope of element X? And X has a Z of 9. So see if you can use that information to figure out which one of those is not an isotope. Okay, it looks like everything's good. Yeah, all right. This symbolism is used to talk about isotopes of atoms, and every atom has an isotope. So let's review what that is. The bottom number is the atomic number. That's the Z symbol up there. That's the number of protons. So lithium, as an example, always has 3 protons. If you take away or add a proton, it's no longer lithium, it'll be beryllium, helium, something like that. But what makes an isotope is the mass number. And the mass number, A, on top, protons plus neutrons. So in this case, this lithium would have 7 minus 3, 4 neutrons, all right? And this is one of the isotopes of lithium. And why that's important is there's also a lithium-6. Now, lithium-6 still has 3 protons, because you have to have that to make it lithium. But top number minus bottom number, 6 minus 3, this only has 3 neutrons. So isotopes are basically just same number of protons, but different number of neutrons. So if you look at this weird symbolism right here then, these lower numbers are the Z numbers. And you can tell, and everybody I think saw this, that yeah, B doesn't have 9 down there, it's got 10. So while the 9s right here would be equivalent to fluorine, because fluorine's number 9 on the periodic table, this one right here would be some isotope of neon, number 10. So that would be how you figure out these different things. Any questions on this? Sweet. Okay, so here's another type of question you'll see with different isotopes, et cetera, et cetera. And this one says, which statement describes the composition of a neutral atom of iron 58? And you can see that lists a bunch of neutrons, a bunch of protons, and a bunch of electrons. Maybe you don't have enough information, you do, but in case it could be, that's always a backdrop and stuff. So see if you can figure out then which one of those would be the correct answer. There we go. Okay. Iron 58. So we're going to build essentially like a version of this kind of format for iron here, all right? So first of all, what is the symbol for iron on the periodic table?
Fe.
Fe, well done. Now, the 58 is either the atomic number down here or the mass number, this number up here. What do you think 58 is?
Mass number.
Mass number. Well done. Clifford just said mass number, right, by the way. But how could Clifford then find the atomic number for iron?
Subtracted by the neutrons.
You're on to the next step, which is really good. Yeah, I liked your answer, Madeline. Yeah, look at the periodic table, because right by Fe, there's that whole number, that blue number, 26, and 26 is the atomic number, which is the number of protons and stuff, the one that goes down there, okay? So yeah, so iron 58 has that 58 is the mass number, the upper number. This is the number of protons, all right? So now, Clifford, we're gonna do what you were trying to tell me, I think. We need to figure out number of protons, number of neutrons, and number of electrons if it's neutral, okay? So is 58 minus 26 the protons, or is 26 or 58 the protons?
50, 26.
26, that's right. This number, the atomic number, is the number of protons, all right? So iron always has 26 protons. You change the number, it becomes manganese or something like that, but it's definitely, iron has to have 26. Now, 58 minus 26 is gonna be protons plus neutrons, which is this number, minus the number of neutrons. And if you do that, let's see if I can do it in my head here, yeah. 58 minus 26, 32. Which number is that? Is that neutrons or electrons? Neutrons, that's right. This number, protons plus neutrons, and we're subtracting the protons, this number, to get this number, which is just the neutrons, okay? Now, if the atom is neutral, all right? What does that tell us about the number of electrons?
It's the same as the no.
Well done, Alan. Yeah, same as the protons. Protons are positive, electrons are negative, all right? And if they're neutral, then these two numbers have to be the same. So on this problem then, answer B is the most reasonable, all right? 26 because it's iron. 58 minus 26, 32. And if the atom is neutral, same number of electrons.
So just clarifying, let's say I have like lithium.
Mm-hmm.
That's +1, right?
It is ionic. Yeah. What happens when it's neutral?
So the neutral ones are like in that middle section, right? That don't have those, like they're not a part of the stairs or anything like that, right?
Whoa. You're trying to make it ionic. You're trying to give it a positive charge. And when you make a compound, it is positive, absolutely. But neutral, all right, this is like raw element, all right? And if it's neutral, then the protons and the electrons will be the same. So you're right, absolutely. Lithium loves to lose an electron and become +1. And iron will lose electrons to become +2, +3, whatever, all right? But all of the elements from helium down to francium, all right, at one point or another, can be neutral. And neutral just means protons and electrons are the same. So in chapter 2, part 2, we did so much making positives, negatives, balance, and blah, blah, blah. But this is actually an example of taking the raw element form and just, and if that's the case, then protons and electrons are equal to each other. Good, excellent. That's a really cool distinction we made. So compounds are more important, arguably, than the elements, right? And that's when you take away or add electrons, whatever. But in this problem with this neutral atom, then the protons and the electrons are the same. Good. Excellent question. Other questions? Here's an element, E. It's got several different isotope percentages, all right? It's got these, so one is 54.5, one's about 15, one's about 30, all right? Here's the numbers that go along with that. So 50+% of the time, 72, 15-ish% of the time, 73, and about 30% of the time, 74. Which of these would be a reasonable value for an atomic weight or molar mass? So remember, the red numbers on the periodic table take all the different isotopes into account, and they use their percentages to get those numbers. So lithium, going back to lithium here is 6.941. And you never have a lithium with exactly 6.941, but you'll have lithium 7s and lithium 6 and stuff like that. So see if you can use this information to find what a reasonable molar mass or atomic weight would be for this element. There's a math way and there's a hand waving way to do this, and either way is okay.
It says it's closed.
Oh, my apologies. Now it's open. Yeah, tell me if I think I'm too cool, but I'm not. Is everybody cool if I talk about this one? Yeah, awesome. So these kind of problems you can do from a couple different ways. All right, I'm going to do the hand waving version first. And in the hand waving version, I pretend what different combinations of the isotopes will be on a number line. So the 72, the 73, and the 74, I'm putting right there. All right. If you had 50% 72 and 50% 74 and almost 0% 73, what would the average number here be approximately?
73.
73, that's right, it'd be right in the middle, all right? If you had 50% of this and 50% of that, then totally it would be very, very close to the middle, all right? But we don't have 50% of 74, all right? We have less than 50% of that. We've got some pretty good amounts of 73 too. So if this is the 50-50 point, I think it's gonna be to the left, all right? It won't be like a lot to the left, but it would be to the left. Now this number, way too close to 72, all right? This would only be possible if you had like 90% 72 or something like that. It definitely won't be to the right of 73, all right? Because if you had 50-50, that would be that value, and we have more than 50% 72. So that's gonna pull it more to the left. So my hand-waving version, I would predict that answer B would be the best answer based on that. Now, some of you are cool with that, and some of you are not, and it doesn't matter if you do or don't like it. But there is another way to do it. You can also do it like we'll do for the isotopes. You can take the mass of the isotope and multiply it by the decimal version of the percentage. So 72 times 0.545 would be your first part. And you'd add it to the equivalent version of the other one. So you'd add it to 73 times 0.156, and add that to 74 times 0.299, and that will also give you an approximate molar mass, and either way is fine. So hook or by crook, you're gonna find out that 72.8 is the best answer here, all right? Either hand waving, thinking about percentages and stuff, but also you can do it the raw math way. This symbol is summation. It means add up all of them. So you add up all of the abundance times the mass. So that this is the mass, this is the abundance. Make sure you use the decimal version and stuff like that. Any questions on that? Sweet. Okay. Here's some examples of ions. All right, now we're going to start getting back to ions again. All right, and the question is, which of these following ions is not likely to form, i.e. we won't see it normally? And this is now when you can absolutely start thinking about columns and stairs and variable charges, stuff like that. So one of those is not something you're going to see on a day-to-day basis, shall we say. Are these all metals or non-metals? Metals, good, that's right. I saw a whisper there, which is fine. So this, to figure it out, this line right there is the metalloid line, and everything above it is a non-metal, and often that includes hydrogen, but hydrogen's over there for a reason. We'll talk about that later. But the important thing here, everything to the left of the metalloid line, which is all of these metals and a bunch of things down here, lanthanides, actinides, all metals. And metals like to be positive. So all of these are definitely metals because of their position on the periodic table, and they're all positive, which is really cool. Now, of the metals, there are some that we know are charged all the time, and there's some charges that we don't know, the variable charge ones. There's only a couple of fixed charge, and those are the 1As and 2As, and then also these stairs, all right? So anything in the stairs and the 1A and 2A is a fixed charge. Now, iron is one of your examples, and it would be maybe difficult to know if this was reasonable or not, all right? But this one then, because it's positive, you could at least say, well, it doesn't seem like it would be weird. I mean, you don't know maybe for sure, but at least you know it is. Iron plus 2 is actually very common. What I was focusing you on here is looking at the other 4, all right? And zinc and aluminum are part of the stairs. Zinc is on the second step, so it's positive 2. Aluminum is on the third step, so it's positive 3. And those are legit. Silver is the first step, positive 1. Sodium is in group 1A, and everything in that category is positive 1. But magnesium is in group 2A, and anything in group 2A had better be positive 2, or else I need to reteach new methods to all of you. Magnesium is a fixed charge metal, all right? Positive 2. In a lab, next to a black hole or the sun, yeah, you can make magnesium plus 3, but it's not something that's going to be stable, all right? Magnesium loves to be positive 2. So yeah, so magnesium plus 2 is the only value that should be legit for this. Questions on that? Now, here's a question about ions, and this is now definitely important. So the question is here, when the strontium plus 2 ion forms, which of those statements would be correct? Now, pay attention here to what the charge is on strontium, group 2A, and also think about what noble gas it's most likely when it loses or gains 2 electrons or 1 electron. I'm giving away too much of the answer here, so I apologize. Anyway, see if you can figure out which of those is legit. Strontium, number 38 on the periodic table. Strontium has 38 protons, and that's what that number means. All right, atomic number of protons, 38. 38 always means strontium, et cetera, et cetera. Now, as we talked about earlier, a neutral atom of strontium will have the same number of protons and electrons. So that means that neutral strontium would have 38 electrons as well, okay? Now, strontium plus 2 is the ion that forms. Group 2A, fixed charge metal, blah, blah, blah. Will the number of protons change? No, good. If you change the protons, you change the atom itself, all right? So strontium would turn into rubidium if it lost an electron. If it gained a proton, excuse me. If it gained a proton, it would go into yttrium, Y, right next door. But it's not going to do that here, all right? This is strontium, just like this was strontium, 38 protons. But what is important now is that we've lost some electrons. Remember, each proton is positive. So before, 38 positive 1 protons and 38 negative 1 electrons gives a charge of 0. But now, in this new iteration, we know we still got 38 protons, positive 1, but the question is, how many electrons do you have to give a positive charge of 2? That's really what this question's all about. So has the strontium atom, the neutral atom, lost or gained electrons to have a positive 2 charge? Lost. This means it has lost 2 electrons. If you do the math here, you can put 36 in here. So 38 times positive 1 plus 36 times negative 1, that goes to positive 2, all right? So when the strontium positive 2 ion forms, it only has 36 electrons. It has lost some. The anions will gain electrons, negative ones. These ones, though, will all lose electrons. So when you look through these examples, they're not losing 1 electron, they're losing 2 electrons to give that positive charge, and not 3 down here either. So if strontium loses 2 electrons, does that give it the same number of electrons as krypton? So yeah, it gains 2 electrons. Oh, so I guess there's only one possibility. I was looking at these up here. Yeah, so it's gonna gain. It's not gonna gain 2 electrons. It's losing 2 electrons. So duh. All right. So answer C. All right. I thought one of the answers was for xenon. So my apologies. Yeah, it's lost 2 electrons. You can always do the math to figure these things out if you want, because protons are positive 1, electrons are negative 1, stuff like that. But yeah, that's what it means to be a positive 2. So strontium metal is actually something that exists, solid, crumbles and stuff like that. But strontium compounds, strontium chloride, strontium nitrate, strontium oxide, whatever, those all have the positive 2 ions, 2 less electrons. And it's usually the positive 2 that are more important than the neutral ones. Questions on that? All right, we'll stop there for today. I'll see you at 110 up in 2501.